Hey, freshman physical science. This is Mr. Arnholt again. It's time for another test, so it's time for another review guide. This time we're doing the forced test review guide. And again, remember, this is not a YouTube video meant for you to watch the whole way through. It's probably going to be over 30 minutes long or so. So your job is to do a problem on the review guide, pause it, check your answer. I will timestamp each problem so that way it'll be easier for you to go guide through the problem. Now, we are going to do all the problems together. So starting with number one, all the way to the very last one. And I'm going to give you tips and guides what to look for. Now, as you can see, the very first problem is going to be a graphing. Create a graph to show the relationship between mass and weight. Mass and weight on planet X using data from the table. Now it tells you to give the title, which is, as we know, is going to be worth a point, the label, the units, and the appropriate scale. And I'll remind you how to do all of those. So before we go on, I hope you remember exactly how all the titles are supposed to be labeled or are supposed to be given. And as always, let's look to, if we have a graph, that means we're going to have a data table. And you should know this from math that the column on the left is going to be the X and the column on the right is going to be the Y. Now, and I tell my students to go ahead and label the left one X sub 1, X sub 2, Y sub 1, Y sub 2. If you do that right now, it'll make everything a lot easier when it comes to finding slope, as you're probably going to be asked to do. So I hope you get that part done. I hope you did that before I even started this. At least all my freshmen, I hope that was the first thing you did. So let's go ahead and start using the graph to figure out what I'm supposed to do. Now, as we know, that the title always has to be given in the phrase, the effect of IV on DV, or the effect of left column on right column, or the effect of X on Y. Of course, that's how my kids have always gone about it. So if we're trying to figure out what goes on our graph, we use our data table. And our data table is telling me that I have mass over here and I have force over here. So those are my two variables. So just go look for those if you're trying to figure out your variables. The data table always gives you the variables, always. So apparently my data table is going to be mass and it's going to be force with the units kilograms and newtons. So is it going to be the effect of force on mass, or is it going to be the effect of mass on force? Remember, the left column, the first one, is always going to be the independent variable, and the second column is going to be the dependent variable. So let's go ahead and give it a try. The effect of mass on force. Check and check. Now, did I get my title done? Yes, I did. Let's check that off. Now let's go to the label, the unit, and the appropriate scale. So as far as labels go, they go on the side over here, and some people put them on the top and bottom, and that's fine. Now, remember, this is the x-axis, so that goes on the bottom. This is the y-axis, that goes on the side, and the bottom is mass. And I'm going to have to erase that because I'm going to have to write a little bit lower, so it's not so much of a problem. It's going to be mass in kilograms, and the side is going to be force, and it's going to be in newtons. I can make that look a little bit prettier, and I should. I'll go ahead and make that look a little bit prettier. Let's get those y's out of the way, though. So it's going to be force in newtons. Okay, now let's do the appropriate scale. Again, freshmen, how do I always figure out the scales? Do I go by ones, 2, 3, 4, or do I go by 0.5, 0.2, what do I go by? And as I tell my kids, it's always the same 3 steps. Step 1, you find the biggest number in your column. So for the x-axis, the biggest number is going to be 0.8. Then we find the number of spots available for that axis. So 0.8 has to fit into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0.8 divided by 10. Well, and then I have to divide that and see what it can fit in there. And the answer is going to be 0.08. And then step 3, I always ask my kids, if I get a silly number, like a silly decimal, should I go by 0.08? And they'd always be like, no, don't do that. So instead, round to an easy number. And the rounding up is going to be to the 0.1s. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1.0. So that scale is done. Let's go to the next one. Same rules apply here. My biggest number is 9.6 divided by my spots available, which is 10, and I'm going to get 0.96. Again, would I want to use that? No, I'm probably just going to round up to 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Once you're done with that, go ahead and start plotting your points. And let's use a different color line. Let's use a purple line here. So my first point is going to be 0, 0. My second line is going to be 0.2 to 0.4. So 0.2 to 0.24. It's about right here. My third one's going to be 4.4 to 4.8. So 4 to about 4.8. Next one's going to be 6 to 7.2. And the last one's going to be 0.8 to 9.6. When that's done, go ahead and draw your line, your best fit line through there. Okay, there I go. Now, is my graph correct? Well, let's do my checklist. Remember, it's out of 8 points. So I'm going to go ahead and let's get a different color pen so we can do a check mark. It's out of 8 points, remember? So title is a +1. First label is a +1. The unit is a +1. The mass is a +1. I got my label unit. And then my scale, I didn't skip any numbers. It goes by the same increments all the time. So +1 here, +1 on that scale, and then finally my lines and data points, +1. That I got all 8 out of 8 points. So that's how your graphs need to be done. Remember, it's always the effect of x on y. So question number 2 comes in, and it says, use the table to graph you constructed to find the gravitational field strength. And basically what that means is it's going to want us to find slope. And like I said at the very beginning, if you would have done, when I started this whole problem, if you would have put y sub 1 and y sub 2, x sub 1 and x sub 2, it would help you along the way. So if you would remember that slope equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So if you have that equation, we can do the guess method real quick, or we can just start from here. We're going to need to know our variables for the slope. We need x1, x2, y1, y2, and they're given to us right there. So x1 is going to equal 0, x2 is going to equal 0.8, y1 is going to equal 0, and y sub 2 is going to equal 9.6. And I'm going to want to find slope. And so I have all my variables. Let's plug it in. And plug it into the equation. And I'm going to have 9.6 minus 0 over 0.8 minus 0. And let's not forget the units over here, by the way. This is going to be 9.6 newtons, 0 newtons, and kilograms. And so when it's done, it's going to be newtons per kilogram. And when it's all said and done, my m is going to equal 12 newtons per kilogram. Okay? Now remember, the gravitational field strength is going to be the gravity of the planet. So apparently the gravity on this planet is 12 newtons per kilogram. Compare that to Earth, which is 9.8 newtons per kilogram. So if an elephant, problem number 3, if an elephant has a mass of 2,000 kilograms, what is its weight in newtons? And it's understood to be what is its weight in newton on this planet X. So I'm going to kind of erase some of the stuff, get it out of our way, just so there's less clutter around here. And that way I can build up a certain idea. Okay. before we do this math problem, we are going to use the guess method. But there's, I want to handle a certain idea. You're going to be given the equations for all these problems, and the equations are probably going to be in the format of the algebra triangle that we've shown in class. And the algebra triangle goes like this. It's going to be the triangle, and it's going to be force, mass, and gravity. That's going to be the triangle, and whichever one you need, you cover up the variable that you need, and you look at the remaining operations. So for instance, if it's asking for force, you cover up the force and you're left with m times g, and that's going to be your equation, is force equals m times g. I have to rewrite that down. If you're looking for m, cover up the m, and it's going to be m equals force divided by g. If you're looking for g, it's going to be force over g equals force divided by mass. So let's read the problem, underline what we're given, and use the guess method. So if an elephant has a mass, what you automatically need to do there is understand that the mass of 2,000 kilograms. That's when you're given variables, and it's asking what is the weight? What is the weight in newtons? Okay. So seemingly, it seems as if we were going to write this problem, we'd probably write on planet X, if an elephant has a mass of 2,000 kilograms, what is its weight in newtons? And you're supposed to understand and comprehend that is already giving you the gravity. So the things that are given to you, first, let's get that back. Let's set up the guess method. G, U, E, S, and S. What's given to you is mass, and mass of 2,000 kilograms, and a gravity of 12 newtons per kilogram. A gravity of 12 newtons per kilogram. And the unknown, well, what is the unknown? What does it want? It wants weight in newtons. And my class has been drilled this, and you have too. Another term for weight is force. Force and weight are the same thing. Remember, weight and force can change, mass cannot. So when you're looking at this problem, your unknown is going to be force or weight. So what's the equation? Cover up force, and you're left with m times g. So you're going to write out the equation, F equals m times g, and you're going to plug it in. F equals 2,000 kg times 12 newtons per kilogram, and the force is going to equal 24,000 newtons. Also on the test, keep in mind that sometimes if we say if an elephant has a mass of 2,000 kilograms, what is its weight in newtons? Sometimes you're supposed to understand that it's going to be planet Earth and you're supposed to know that planet Earth has a G, or a gravity, of 9.8 newtons per kilogram. So we're going to have to clarify that for you. So problem number 4. If a pot of chili has a weight of, let's choose it with a different color. If a pot of chili has a weight of 19.6 newtons, what is its mass? Okay, we are to understand that it wants mass and we're given force. Well, go to the triangle. If it wants mass and it gives us force, well, then we must need 2 out of the 3. Well, then we're supposed to understand that we're given gravity, and we're supposed to understand gravity to be 9.8. So let's plug in the variables and figure out what we need. Again, doing the guess method. Our givens are going to be, let's get out of there. Our givens are going to be force equals 19.6 and gravity equals 9.8 newtons per kilogram. Now, that means we're going to want to find mass. M equals the question mark. And what's the equation? Well, you cover up the M with your finger, and you're left with M equals F over G. So the equation is M equals F divided by G, and then we plug them in, we substitute. M equals 19.6 newtons divided by 9.8 newtons per kilogram. And we're going to be left with, when we get done, the math is going to read mass equals 2. But what's my unit? If you need help, look throughout the test that mass was always in kilograms. Okay, so those who forget the units, use the test to help you. Go find somewhere in the test where it reads mass of something, something, and you notice it's going to be in kilograms. Now, you should already have that memorized, but if you still need help, if you forget the different units, find them in the problems, and they will help you out. Okay, problem number 5. We're going to summarize each of Newton's 3 laws. And for my class, what we did is we made a little logic box or logic train, and how each of them fed into another one. But what we're going to give is we're just going to summarize with a couple words. So Newton's first law was the law of inertia. Let's get it a different color. Let's go blue. It was inertia. And what that meant was the idea of an object won't move unless the forces are balanced. So we have these balanced forces, and the objects stay in their motion until the forces become unbalanced. So that is, objects stay in their motion until forces are unbalanced. Another way to say this, class, is that objects resist a change in motion. So be prepared for that. I think that exact wording is on the test. Objects resist a change in motion. So the second one, and this one's pretty simple. If the first law is objects stay in motion unless the forces are balanced, the second law is all about calculating the unbalanced forces. So the second law is force equals mass times acceleration, or acceleration equals force divided by mass. So, and then finally the third law is action-reaction pairs. It's every reaction has an equal and opposite reaction. Now, students, you're going to be asked this. If something is pushed with 5 newtons, how much is going to be pushed back? 5 newtons. That's what the word equal means. Don't miss this. It's a simple problem. Just don't miss it. Okay, so let's review these 3 laws real quick, and I want you to see the logic flow. So Newton's first law was that an object is going to stay in motion unless there's a unbalanced force. And then he's like, well, how much was that force that unbalanced it? And then so the Newton's second law is all about calculating those forces based off the mass the object had and how much it moved or accelerated. And the third law was building on top of that. If there was a force acting on one object, then there must have been a force acting on the other object as well, equal and opposite. Remember the spring scale for this. The spring scale lab did a really good job where never once in our spring scale lab did we pull one spring and the other one wasn't also pulled to the exact same amount. So number 6, we're going to describe what happens to a moving object in each of these scenarios. So a net force acts on an object in the direction of its motion. So a net force. Now, my class has a problem with understanding what these phrases really mean. When we say a net force, another way of saying a net force is unbalanced. It means there's an unbalanced force. That there's a net force greater than 0. That's what we're saying. If there's a net force, and we are saying a net force greater than 0. So if I am pushing, say I am pushing a hockey puck. I'm a hockey puck and I'm pushing it this direction. And then I add another greater force in this direction, the direction it was already going. Well, what's going to happen to it? I'm not opposing the motion, am I? I'm helping the motion. So what should it do? It should speed up. Now look at this, a net force in the opposite direction. Like, I don't know, friction? By the way, every one of you should know that friction works in the opposite direction. That's probably going to be a question later on. Don't miss it. So now the object, the puck or so, was traveling this direction, and then another force, say a guy swings a hockey puck the other direction, and it opposes the motion. Well, do you think it's going to speed up if you hit it in the opposite direction? No, it's going to slow down. So it slows down. And then finally, a net force on an object is zero. Go back to Newton's first law. The object will stay in motion until the forces are unbalanced. So if there's no force to unbalance this, if there's no force to unbalance it, it's going to keep going in that direction at that speed until something stops it. Okay? So it's going to be stay doing what it was doing. Okay? Problem number 7. Describe what happens to an object that is sitting still. Okay? That is sitting still. That means it's not moving. It's stationary. Okay? So I got the hockey puck on the ice, and it's not moving. No motion left or right, forwards or backwards. Again, what does the word net force mean if this would stop rotating? The word net force means unbalanced. Back to over here. Net force means unbalanced. So Newton's law says, first law says, if the forces are balanced, it will keep doing what it's doing. And right now, it'd be sitting still. If the net forces become unbalanced, it will accelerate. So we should expect it to accelerate. And that just means change its position. Remember, acceleration is both changing speed and direction. So we expect it to accelerate. Now we have a net force of 0. Remember, an object in motion will stay in its particular motion. Right now, the hockey puck is sitting still. Its particular motion is sitting still unless there's an unbalanced force on it. A net force of 0 is a balanced force. So since there is no balanced force, it will stay still. Okay? Number 8, when you slam on the brakes in your car, what happens to someone not wearing a seatbelt? Explain with one word. What's that one word that describes what happens to them? Or what's the phrase that sums up Newton's first law? What word is that? And the answer is inertia. Okay? So what happens because of inertia? They fly forward until they crash into an object, until they crash into a part of the car. Usually the windshield or another window. So please wear your seatbelts. Number 9. If you find a slope of the force versus mass, what do you find out about the planet? Force versus mass. Did we do that somewhere? Is there maybe in the first problem which we found the slope of force and mass where it was force over mass. Did we find that somewhere? Yeah, let's go to the top problem. What did we get when we got force over mass? And we got gravity. You found that planet's gravity. So the answer is gravity. Now, this is where I need to explain some things. The other term for gravity is acceleration due to gravity. Let's go back and look at that algebra triangle, and this is a good time to discuss that algebra triangle. So that algebra triangle, as we said earlier, was, let's change up the coloring here. We've done that a couple problems now. That algebra triangle, let's make that a little bit, we want to block up the other words. That algebra triangle was F m times g. Well, g is gravity, but what gravity really is acceleration. So another way of saying that is force, mass, and acceleration. G and A are the exact same things. Let's not get confused on this. G and A are the exact same in this equation, okay? Let's not get confused. They are the exact same. So acceleration of gravity and gravity mean the same thing. We call it G whenever it's the planet that's making objects move. We just call it acceleration whenever it's any other a force. So question number 10. What does it mean to say that forces on an object are balanced? What does it mean that forces are unbalanced? I think I already gave us this answer. So if we go back up, what had I written earlier? Net forces are unbalanced, and so when it says, what does it mean to say that forces are balanced? That means, so balance means all forces in all directions cancel each other out. Or they are equal to each other. Same thing. And what does unbalanced mean? That means the opposite. That one force in one direction is greater or less than, or let's just say unequal, is unequal to another force. Number 11. What is the relationship between friction and motion? What is the relationship to friction and motion? Friction and motion act in opposite directions. That question has been on 3 different quizzes in some form or another. They act in opposite directions. Friction opposes motion. Now we all know that. We all know that. I don't know what's going on there. Friction opposes motion. So if my car is driving left, friction is going right. So question number 12, how do you find the force acting on an object when given the mass and acceleration? How do you find the force on an object when given the mass and acceleration? This is asking you for the equation. So just give us the equation. So let's look over here. It wants force, and we're given, so our unknown is force. So G, U, E, S, and S. When we're given mass and we're given acceleration, it wants to know force. Well, cover up the force cover up force, and then see what we're left with. And we're left with m times g. So the equation is going to be F equals m times a, or m times g. Since it asks for acceleration, let's use acceleration. Okay, problem number 13. If a cart with a mass of 50 newtons, this is a typo, so I'll put this in on your paper, with a mass of 50 newtons, it really means kilograms. If a cart with a mass of 50 kilograms is pushed with a force of 200 newtons, what is the acceleration? Okay. Every freshman should have caught that mistake, because you should know that mass is in kilograms, force is in newtons, and the acceleration is newtons per kilograms for us so far. So let's do the guess method. G, U, E, S, and S. We are given two variables. M equals 50 kilograms and F equals 200 newtons. And we're looking for A. So what's the equation going to be? We'll cover up A. A equals F over M. So A equals F divided by M. Substitute in A equals 200 newtons divided by 50 kilograms. And when it's all said and done, A is going to equal 4 newtons per kilogram. But that's really a gravity thing. Acceleration is going to be meters per second squared. And we would, of course, help you with those units. Meters per second squared. So we'll have those listed out for you. Okay, problem number 14. How do you find an object's weight? How do you find an object's weight? Well, your job is to realize that weight is a synonym for another word. In my class, I spent a long time explaining these synonyms. Synonym for gravity and acceleration. Gravity is acceleration. And what's the synonym for force? What word means weight? The answer to that is force. They mean the same thing. So go to our equation. If weight equals force equals, cover up the force, and it is F equals M times A, or M times G. Now, how does your weight on the moon compare to the weight on Earth, and why? I have warned my class over and over, and it's been on all 3 quizzes. The weight and mass question has been on all 3 quizzes, and we began the unit with this question in our questions of the day. Please, no students miss this. Remember, weight is the effect of gravity on your mass and can change, and mass is the number of particles that make you up. Mass can't change. Weight can change. So let's go back and answer this question. How does your weight on the moon compare to your weight on Earth? Again, weight is the effect of gravity on their mass. So the more gravity, the more weight. So your weight on the moon is less because moon's gravity is less. Now, if we were to reverse the question, how does your mass on the moon compare to your mass on Earth? The answer is the same. That was question number 1 on our quiz from Friday, October 12th. So now let's go to what happens to your weight as you go farther and farther from Earth, as you travel farther and farther from Earth. There's a typo there. Well, let's look at this one. If your weight is less because gravity is less, what happens as you get farther from Earth? The gravity weakens. So as gravity lessens anywhere, your weight lessens. So what happens? Weight decreases because gravity decreases. That was from quiz 1. Okay, what does F sub G stand for? We all should know this. F sub G stands for gravity. What does F sub F stand for? We should all know that it stands for friction. Now that's whenever you have motion. So anytime there's motion, unless you're in space, or we tell you to ignore it, there's got to be friction. When would be a scenario in which we would tell you to ignore friction? Maybe like the skier in the air, we would tell you to ignore air resistance, so ignore that friction. What is F sub A? Well, that's applied force. And remember, that's the generic push-pull. And then what is F sub T? That's tension, and it only exists if there's a rope or a string. Don't confuse F sub T and F sub E. A spring is not a rope. So a spring is F sub E for elasticity, and a rope is F sub T for tension. And then finally, the last one, F sub N, is support or normal. Remember, class, that support isn't always up and down. Support is always perpendicular to the surface. So if the surface is flat, then support's right up and down. If your force is angled, support is at an angle. Just hope we don't forget that. Okay, question number 18. We're almost done. Question number 18. Draw a force diagram of the object. Tell if the forces are balanced up or not. Now, and how can we know? And the answer to this is really simple. Look at the words it's telling you. Constant, resting, speeding up. That should tell you whether the objects are balanced or not. So my class knows there's 6 rules or so that I go when we're doing these force diagrams. In order to do them, we need to list out all of the 7 forces. We have F sub G, gravity, F sub A, applied, F sub T for tension, F sub B for buoyancy, F sub F for friction, F sub E for elasticity, and F sub N for support or normal. So when we're drawing a force diagram, first things we do is we find perspective. What am I looking at? Am I looking at the human, or am I looking at the ball? Am I looking at the bird, or am I looking at the stand, or am I looking at the cage? Am I looking at the man, or am I looking at the cart, or am I looking at the horse, or am I looking at the man and cart? Perspective is the most important because that changes whether or not I have different applied forces or not. The second thing I do is I draw it as a dot. The third thing I do is I list all the forces I see acting on my object based off perspective. So I list forces. Then step 4 is I draw the forces in the correct directions. 5, and again, people have different rules. I'm just doing a step by step for me. 5, I make sure I draw my forces as arrows. Sorry, and then step 5, I make sure that my arrows are the correct length. So I care about the magnitude of my arrows, the magnitude of the arrows. And step 6 is I label them with either the source or the agents, or I just label the forces. So let's do number 1 with the ball. Okay, so step 1, it's telling me my perspective isn't the human, it is the ball itself, the ball. So I draw the ball as a dot, and then I go through everything that's acting on the ball. So let's go through my checklist. Is gravity acting on the ball? Check. That's going to be one of my forces. So F sub G. And now gravity is the only non-contact force. So if I don't have gravity, if I have gravity is the only thing that exists, even if it's not touching it. Everything else, you physically have to have something in contact. So if I'm looking at the ball, is anything touching it? No. So that means there's no applied force. So let's get out of there. There's no applied force. There's no rope or string, so there's no tension. It's not floating, so there's no buoyancy. It's not, and again, I know there's air resistance, but we're going to ignore that. There's no friction, and there's no spring or rubber band, so there's no elasticity, and it's not sitting on the ground or sitting on a surface, so there's no normal. The only force is gravity, and I list the forces, check, and then I draw the forces with the arrows in their direction. Gravity always works down. I make sure the magnitude is correct. Now here it doesn't really matter as long as it's balanced, and there's no force to unbalance it. And then I label it F sub G, and usually we put the source or the agent, and that's going to be the Earth. So there's my force diagram. Now let's draw the force diagram for the resting bird. Step one, I'm looking at the bird. The bird is the only thing I care about. So let's not make this too complicated. The bird is the only thing. Let's make this yellow, see if the yellow will stand out. Then I draw the bird as a dot. And then I list my forces. Let's go through the whole 7. I have gravity, check. So F sub G. Now if I'm not falling down, then I'm being supported. So I have F sub N. Now F sub N is a contact force. What's physically touching the bird? This stand is physically touching the bird. Is there anything else? Is there a rope for tension? No. Is it floating in the air for buoyancy? No. Is it moving? No. Is there a spring? No. And is there anything else touching it, like a finger or another bird or anything pushing on it? No. So applied. So of all my 7 forces, it's only got 2 forces. It's got gravity and support. So the arrow for gravity is down. Now remember, support, F sub G. Now remember, support isn't always straight up and down. It isn't always completely vertical. It's 180 degrees or perpendicular to the surface. And how do you know? Well, you make a square on that surface and you draw up. Well, that's an upward arrow, so this one it is going to be 180 degrees. Then we look at the magnitude of our arrows. And this is what the whole point of this question is. Are they balanced or not? Well, is this that bird moving up and down? No, which means its gravity and its force and its support got to be equal to each other. I know this isn't perfect, but right now, relatively speaking, they're equal to each other. So we got F sub N, F sub G. What is the agent of gravity? Earth. What is the agent of the support force? That is going to be the pedestal or the stand. And there we are. Everything's taken care of. Finally, the horse speeding up. Let's have the horse speeding up. This one, it's the horse we care about, okay? It's the horse we care about. It's not the buggy. It's not the man. Okay? What force are acting on what force are acting on the horse? So we draw it as a dot and we go through our list. Okay? 1. Is there we got a perspective, we draw the dot, let's go through our forces. Is there gravity? Yes. Okay. Is it floating in the air? No, so there's some kind of support, F sub N. Is there a rope or some kind of thing on the horse? Yeah, there's these halters, and there's a lead rope there, so F sub T. Is it floating? No, so there's no buoyancy. Is the horse moving? Yes, there's friction. And then, is there a spring of some kind on there? No. Is there anything else? Now, is there something touching the horse? Anything other than the halter and the lead rope that's on there? Nothing. So there's no applied force. So there's no applied force, there's no buoyancy, and there's no elasticity. It's only F sub G, F sub N, F sub T, and F sub F. So those are our 4 forces. Let's draw them. So step 4, let's draw our forces. Gravity is going to work down, F sub G. Support's going to work up, F sub N. Now, is the motion constant for up and down? Yeah, so my gravity and my support are going to be equal to each other. Now, it says it's moving. Well, I'm sorry, there's going to be applied. It's going to be applied on the ground. So there's going to be applied on the ground. Otherwise, it won't be able to move forward. There's a 5th one. Sorry about that, guys. So you've got the tension from the buggy and you got friction. But then you got this applied force working this direction. The applied force is pushing the horse in a right to left direction. Okay, F sub A, and that's the horse itself. That the horse is making itself move. And then you have, or you could say the ground is making it move, but really the horse. And then you have F sub T, and then in the same direction that the tension is pulling the horse back, you have F sub F for friction. Now, magnitude-wise, if the horse is speeding up, Newton's law says that the forces can't be balanced. So one's got to be bigger than the other one. And since it's speeding up, the applied force has got to be bigger than the friction and tension. So are the forces balanced? Well, for the ball, no, the forces weren't balanced because the motion was constant. Oh, I'm sorry. It was left to right. I apologize. I just looked at it. It's looking at the left to right motion, not the up and down motion. I apologize. Left to right. Is there anything left and right of this? No. So the speed of the ball is constant. So the forces in that way are balanced. It's balanced left and right, but it's not balanced vertically. Okay. Next, the bird. Is the forces balanced? Vertically and horizontally, the bird's balanced. Now, for the horse, vertically, the forces are balanced. But for horizontally, no, because it's speeding up. Okay. So for this one, vertically, let's do this. Vertically, not balanced, but horizontally, it is balanced. There's not 2 S's in yes. For the bird, vertically, it's balanced. Horizontally, it's also balanced. And for the horse, vertically, it's balanced, yes, but horizontally, it is not balanced. Okay, let's go to number 19, and then we're almost done. I hope you guys have been pausing through this. Let's take a couple more questions on here. Two identical metal balls are hanging in the gym. They're identical metal balls, and they're hanging in the gym. What is the mass of each of the balls? Well, they're identical, so their masses must be the same. They're identical. So if this is 5 kilograms, this one also has to be 5 kilograms. So they're each 5 kilograms. Okay? What is the weight of the balls? Remember, another word for weight is force. So it's asking what is the force? Now that's a calculation problem. Okay? It wants to know the force. Remember, the mass equals 5 kilograms, and it's on planet Earth, so the gravity equals 9.8. So when you do this, what is going to be force is going to equal F is going to equal M times A. F is going to equal 5 times 5 kg times 9.8 newtons per kilogram. And so the force, or the weight, is going to equal 5 times 9.8, so a little bit under 50. 5 times 9.8, it's going to equal 49 newtons. Now, what is the force or the tension on each of the strings? So for the first one, oh dear, the forces have to be balanced. Each of these are standing still, okay? So each one of these has a balanced force. So for each one, I have 49 newtons being pulled down. 49 newtons being pulled down. Okay? This first one, the first one has 2 strings coming up. If it's balanced, that means 49 newtons are being pulled down and 49 newtons are being pushed up. But there's 2 strings here. So what's that going to be? Well, each of those strings are going to bear the 49 newtons. You're going to share the load. So this one's going to be 49 divided by 2, basically. So it's going to be 24.5 for this string and 24.5 newtons for that string. While this one over here is only 1 string, and that's going to be all 49 newtons for that 1 string. Okay. What is terminal velocity? Now, we've talked about this in our class. And I'm going to use 3 diagrams, and I've done this in class before too. So imagine you're in an airplane. There's a little plane, another little wing, here's my windows, and you're diving. And you're jumping out, you're skydiving out. Remember, Newton's first law says that an object in motion will stay in motion unless it's an unbalanced force. When you're on the plane, your vertical motions are balanced, right? F sub g and F sub n are balanced. When you jump out of the plane, there's no longer support force, and the only force acting on you is gravity. Are you balanced there? No. And since you're not balanced, you're going to accelerate. This is going to cause you to accelerate, which means speed up in this case, downward. But as you accelerate, you're going through the air faster and faster, and you hit more air molecules. And those air molecules push back up on you. So as you fall down, you start being pushed up just a little bit by the air resistance. So that's F sub, and it's an applied force there by the air resistance, F sub A. Or you could call it F sub F for friction, but F sub A. As you fall faster and faster, again, this is still unbalanced, so you're still getting faster, right? As you fall faster and faster, you hit more air molecules per second. So more air molecules are hitting you per second, so there's more objects creating a larger force on you. So that force gets larger and larger. It's still not balanced yet, so it's F sub g, still not balanced, you're still speeding up. But finally, you speed up so fast that the air molecules are creating enough force on you that it's balanced out gravity. Now, here's a misconception. That is not saying you and gravity, that you're not falling down anymore. All that means is you're not speeding up. So terminal velocity it's the velocity in which an object stops speeding up towards the ground. Is it still going fast? Yes. It didn't slow down. It just stopped speeding up. You see how they're balanced here? That means it's going the same speed it was at this point in time. Not speeding up, but also not slowing down. That's what terminal velocity is. A couple more and then we're done. And I thought we were already, but we're not. Let's do blue. If a wadded up piece of paper and a flat sheet of paper are dropped in the classroom, which will hit the ground first? So I have a flat and a wadded sheet of paper. Well, we did this in my class. We did we saw the bowling ball and the feathers dropped in a vacuum, and then without a vacuum. When they were just dropped, the bowling ball hit the ground first because it had had a larger mass and less air resistance to the mass, while the feathers floated slowly. But when they were dropped in a vacuum, they both dropped at the ground at the same time. Well, what was the difference? In the first scenario, there was air molecules pushing up on it. The second one, there wasn't any air molecules. So with all things being equal, if there's air molecules pressing up on this, the air molecules will slow the flat one down and not bother the rolled up one. So what's going to happen? Flat one will hit the ground first. due to air resistance. Okay, a penny is dropped into a wishing well. What is the penny's acceleration? Well, what planet are you on? Earth? Well, what's the acceleration? Let's go back up here. What is the acceleration due to gravity? So that's going to be 9.8 meters per second squared. Okay. So if a penny has a mass, by the way, this is going to equal A, right? So if the penny has a mass of 0.003 kilograms, what is the weight? And what's another word for weight? Force. So it wants force. And let's use the guess method. G, U, E, S, and S. From the previous problem, you're given A equals 9.8 meters per second squared. You're given mass equals 0.003 kilograms. And you're looking for force. And the equation is F equals M times G. So plug it in. F equals 0.003 kg times 9.8 newtons per kilogram. And when I solve it, 0.003 times 9.8 is going to get you 0.029 newtons. So F equals 0.029 newtons. So if it takes the penny 3 seconds to hit the bottom of the well, how deep is the well? I don't know if we actually have that problem on the test, so I think we're fine with that one. We don't actually have that problem on the test. And then finally, yeah, that's a time question. We're not going to do that one. Draw the force diagrams for the bow and arrow, and how does the force on the bow from the arrow compare to the force on the arrow of the bow? Again, this is an action reaction, but let's draw the force diagram for the bow and for the arrow. So that's two force diagrams. Okay, step one, perspective. Let's do the bow first. Then let's do the arrow over here. Let's draw some different ones, different colors. So for the bow, we care all about contact, okay? And for our purposes, I don't think it wants us to really care about gravity right now because it's blank. It's been held up. So it wants us to look at all the contact forces. So draw our dots for the bow. What's touching it? I think it's the bow or the string. I think it wants the string, but for the bow and for the arrow. So looking at the bow, what's touching it? So we have an applied an F sub A from the arrow itself, right? And we have, of course, F sub G and F sub N are holding it up because it's not moving. And then there is I'm assuming a hand pressing the other direction there. So we got F sub G, F sub N, and then the arrow is pressing back that direction. And there's another force. If this isn't moving, then the forces have got to be balanced, right? So we've got the arrow pressing back in that direction, being pressed back over here, and there's something else pressing and keeping it forward. There's it's called the tension force over there. So either way, there you have the arrow pressing back this way, and that's what we care most about here. And let's do the arrow over here. The arrow, you got gravity and support, been holding it up. But what we really care about is that if the arrow is being pressed this way, then the bowstring is pressuring on the arrow with the exact same amount of force the other way. And let's actually make it a different color, because that's the entire point of this. That's the entire point of this question, is in Newton's third law. So if the arrow is being pressed down this way, then the string is pressing on the arrow with the exact amount of force in the opposite direction. So this arrow, this arrow right here better equal the applied force of the string. They better be the same amount. So this is going to be an F sub A, and that's going to be the bowstring itself. Okay, and what's keeping that there is going to be the applied force of the bow. And I guess the hand is holding it in check. But either way, what we're looking at is this right here. Let's highlight this right here. This better be equal to that applied force right there, because it's equal yet opposite reaction. So explain, how does the force on the bow from the arrow compare to the force on the arrow on the bow? They are equal. They are equal and opposite. Okay, I hope that helps y'all with this. Good luck on the test.